Okay, so what if you could give an AI a new brain for any topic you wanted? Like popping a new cartridge into an old video game console. Well, that's the incredible promise of a new technology called Memory Decoder, and it's aiming to solve one of the absolute biggest challenges in AI today.
So let's just dive right in. Why is AI memory such a huge deal? I mean, why is it so hard? Well, it turns out that giving an AI a memory is nothing like, say, giving your computer more RAM or a bigger hard drive. It's a totally different and, frankly, way more complex problem to crack.
Think about it like this. A regular computer's memory is perfect, right? It's static. You save a file, you open it a year later, it's exactly the same. But for an AI, memory has to be contextual. It has to be complex. It needs to be a lot more like a human's memory, where it can connect ideas and understand all the nuance. And that's a massive challenge that current AI is still really grappling with.
And that gets to the most crucial point here. The goal isn't just to give an AI access to a giant database. That's easy. That's just giving it a library card to look things up. The real prize, the holy grail, is to actually encode that knowledge into the model's internal workings, to give it a true long-term memory that it can use intuitively.
So, how have developers been trying to solve this up until now? Well, it turns out the current solutions have forced a really fundamental dilemma on anyone trying to build a specialized AI.
Right now, if you're a developer and you want to adapt a general AI to a specific area like medicine or finance, you're pretty much stuck with a tough choice. You've got two main options: DAPT on the left and RAG in the middle. But both of them, they come with some really serious trade-offs.
First up, you've got DAPT. That stands for Domain Adaptive Pre-training. And this is basically the brute force method. You retrain the entire model on all this new specialized data. As you can imagine, it is incredibly expensive and it takes forever. And even worse, it suffers from something researchers call catastrophic forgetting, where the model learns the new stuff but then forgets some of its original general knowledge. Not great.
Then there's the other option, RAG, or Retrieval Augmented Generation. Now, this method is way more flexible. It keeps the original model totally intact and just pulls in relevant info from an external database whenever it needs it. The problem? It is so slow. All of that searching during a query adds a ton of latency, which just makes it clunky and impractical for a lot of real-time applications.
So you're stuck, right? You've got costly and forgetful on one side, or flexible and slow on the other. This is where we get to the breakthrough. What if there was a third way, a truly plug-and-play memory?
And here it is. Enter the Memory Decoder, or MEMDEC for short. So what is it? It's a small, separate part of the model that's pre-trained with a really clever goal. It learns to imitate an external data retriever. Essentially, it becomes this compact, super efficient, self-contained memory module that you can just plug into any compatible large language model.
And this is the aha moment. Remember those other methods? DAPT forces you to do a full, costly retraining. RAG has to slowly go search some external database. But look over there on the right at MEMDEC. It simply interpolates. It just blends its specialized knowledge directly with the base model. It is the elegant third way that avoids all the problems of the other two.
Okay, so how does it actually learn all this specialized knowledge? The secret, as we just mentioned, is its pretty genius ability to mimic a retriever.
The researchers use this great analogy to explain it. Think of an AI model as having two main parts, a big, heavy lifting part and a small part that acts like a translator. Now imagine you train only that tiny translator part on the entire Harry Potter series. Then you just plug that little specialized module into the main AI. Suddenly, the entire model understands Hogwarts. That's the core idea here.
And it all comes together in this two-stage process you see here. In that top half, during pre-training, the memory decoder basically learns to think like a traditional retriever. Then, in the bottom half, when it's actually running, it works in parallel with the main LLM to create a final output that's an expert in its domain, all without any slow external lookups.
Let's break that down just a little bit more. So step one is pre-training. The memory decoder is trained to copy what a classic retriever would find. So it's not just memorizing documents, it's learning the deep-down patterns of information in a specific field. Then, step two is inference. This pre-trained MEMDEC runs alongside the base model, and their predictions get combined. It's simple, elegant, and super efficient.
So, the theory is brilliant, right? But does it actually work? Well, when researchers put it to the test, the results were, honestly, they were staggering. It turned out to be smaller, faster, and smarter.
Okay, take a look at this graph. Perplexity is basically a measure of how confused a model is by new information. So lower is always better.
That solid red line shows that, yeah, bigger models are generally better. But look at that blue line way down at the bottom. That's a model with MEMDEC. It gets a dramatically lower perplexity score, which means it's getting way better results with far fewer parameters.
And this right here, this is the killer statistic. A tiny 500 million parameter model, when you give it a memory decoder, can actually outperform a massive 72 billion parameter model on these specialized tasks. That is over 140 times the efficiency. I mean, that's not an improvement, that's a monumental leap.
But what about speed? Remember that big latency problem with RAG? Well, MEMDEC absolutely crushes it. The red line here, another method, more than doubles the processing time. The green one is a bit better, but still adds a lot of overhead. But look at MEMDEC, that blue line. It adds a mere 1.2x overhead. It's almost as fast as just running the base model all by itself.
And here's where that whole plug-and-play power really shines. The researchers took one single small memory decoder and plugged it into a whole family of models, from a tiny 500 million parameter model all the way up to a 72 billion parameter giant. And just look at the results. It consistently and dramatically improves the performance for every single one of them. One memory, many different models.
Okay, so let's zoom out from the charts and the data. What does this all mean for the future of AI memory, and why does any of this really matter?
What this really points to is a future for AI that's fundamentally modular. So instead of building these giant, monolithic AIs for every single purpose, we could have one great general-purpose AI and then a whole library of these specialized memory cartridges. Need a legal expert? Plug in the law cartridge. A financial analyst? Swap it out. It's a total game changer.
The researchers themselves put it best. They call this a new paradigm for domain adaptation that fundamentally reimagines how we specialize language models. This isn't just some small improvement, it's a completely different way of thinking about how we build intelligent systems.
Which leaves us with a final fascinating question to think about. As this technology gets better and better, will every general-purpose AI soon come with its own library of plug-in memories, ready to become an expert in literally anything at a moment's notice? The future of AI might just be plug-and-play.